Post-processing is a way to apply visual effects to your entire rendered scene. Think of things like color correction, God rays, chromatic aberration, overlays, and so on. In this video, we'll explore how to add post-processing effects in Three.js. We'll start with native support, then level up using PMNDRS's post-processing library for more effects, more control, and better performance. I've set this up as a vid project, which is super easy to do with the command npm create vids and npm install 3 to bring in Three.js. Here's a quick rundown of the setup. A black background and no margin, and of course not forgetting to attach our script. In the script, we import Three.js, set up the scene, camera, renderer, and throw in orbit controls so we can move things around. For lighting, we'll be using ambient and directional lights. The scene itself will have 3 main things: a sun, a planet, and a star field. The sun is just a plain white sphere using mesh basic material. For the planet, I'm using a texture of Mercury mapped onto a sphere. And for the star field, I've got this image of a starry sky that wraps around the whole scene. The animation loop handles the planet's rotation, and I've also added some code to make sure everything resizes properly when you adjust the window. If you're new to this and want a deeper dive into setting up scenes and rendering, I go over most of these basics in my introduction to Three.js series. Feel free to check that out. Alright, let's now get into post-processing. The first thing we need to do is import a few things, starting with the effect composer, which is basically the effects manager, then the render pass, which gives us a base image of the scene to apply effects on. Let's scroll down just before the animation loop and create an instance of the effect composer, passing in the renderer. The composer uses something called passes. Each pass is an effect. The only one that doesn't change the image is the render pass, but it's important to include it first because without it, there's no image to work with. You add passes to the composer like this, starting with the render pass. Then in our animation loop, we'll swap out the usual renderer.render call with composer.render. If you run the code now, you should see your scene look exactly the same, which is perfect. We've got the setup ready to start layering on some effects. Let's start with anti-aliasing effects, which helps smooth out those jagged edges around objects. First, we import the effect we want, in this case SMAA pass, which stands for Subpixel Morphological Anti-Aliasing. It's lightweight and works really well, especially if you care about performance. Once we import it, we initialize it by passing in the width and the height of the render area. Since we are rendering full screen, we just use window inner width and window inner height multiplied by the device's pixel ratio to get a nice, sharp result. Finally, we add that pass to the composer. And if you look closely, you should see the edges around the planet are now a lot smoother. Subtle, but definitely an improvement. Now, what if you want to create your own post-processing effects? Something that isn't already built in. What you need is the shader pass. It lets you write custom shader code and apply it just like any other effects. As an example, let's make the whole scene render in grayscale. We set up a custom shader using shader material class as the first argument. The second argument represents the name of the uniform that will hold the rendered image from the previous pass. Ensure it is identical to the uniform you're using in your shader. That way Three.js knows where to plug in the image. Now in the vertex shader, we don't need to apply any transformation matrices. The position data is already correct, and the default matrices are basically identity. So we can skip these calculations and save a bit of performance. What we do need is the UV coordinates for each pixel, so we pass those over to the fragment shader using a varying variable. Then in the fragment shader, we sample the color from the image using UV coordinates, average the red, green, and blue channels, and assign that average to the GL frag color. Add that shader pass to the composer, and now the scene renders in grayscale. Note that pass order matters. The composer runs effects in the order you add them. So here, anti-aliasing happens before our grayscale effects. It doesn't matter that much in this case, but some effects might give you different results depending on the order in which you add them. Let's now take a look at a case where you might want to consider that party library. There is a commonly used effect called the Unreal Bloom Pass, which makes objects glow. The effect looks great, but you can't pick which objects glow. Everything glows unless you do a bit of workaround. That is, render the scene twice, first with dark materials on the non-glowy objects, and then combine that in a second render. With the post-processing library, we can skip all that using Selective Bloom. After installing, import its effect composer, render pass, effect pass, and Selective Bloom effects. Note that the effect composer and render pass are not the same as the ones from Three.js. Mixing them will throw errors. This time, instead of just adding effects directly to the composer, we'll be adding them to the effect pass, which has performance optimizations, and then add the effect pass to the composer. Let's get rid of Three.js effects. We can leave composer and render pass set up, it works just the same. Then we create a Selective Bloom instance. You provide the scene, camera, and bloom parameters. The key part is the selection property, which you can use to pick which objects glow, and in this case just the sun. Add the effect to the effect pass, and then add that to the composer, and only the sun glows. This project's GitHub has a link to a demo project where you can get hands-on with the effect parameters. There is another effect called the God Rays effect. It not only gives the sun bloom, but adds some beautiful volumetric rays. You pass in the camera, the glowing object, and a few parameters. These are the ones I thought look great. It's even better than the bloom effect. I love how the light bleeds into the planets. We can even tweak the sun's material color and give it a blue-purple haze. Speaking of color, yes, there is support for color grading too. The library even works with lookup tables, which are used to match your scene's colors to a specific mood. For example, if you're aiming for a cool cinematic tone, you can use an LUT that boosts blues, greens, and cyans. These LUTs are easy to find online. I've downloaded a free LUT pack from Shutterstock, which comes in cube format, exactly what we need. And to use them, import the LUT loader and the LUT 3D effects, then load the file. Let's go with Blue Hour. Create a new instance of the LUT effect using the loaded data and add that to the effect pass. And here's the result. The planet now has a vibrant blue, and even the sun's bloom has shifted to match. Let's make it look as if we are in space taking video. I've got a camera overlay image we can use with texture effects, and we'll throw in a bit of chromatic aberration, maybe from cosmic radiation or something. The possibilities here are endless. If you're following along, I'll leave it to you to apply depth of field. Try shifting focus between the planet and the stars in the background. One last thing I want to show you is how to write your own custom effects that works with the effect pass. You do that by extending the effect class. In the constructor, you call super, passing in the effect's name, the fragment shader, and any uniform you might need. For now, let's keep things simple and just recreate the grayscale effects. No uniforms needed. You don't have to write a vertex shader, but the fragment shader is a bit different. Instead of using main, you define a main image function. It takes 4 arguments: the input color from the previous pass, the UV coordinates, and the reference to out color, where you write the final pixel color. If you need to make use of the unmodified scene render, you can declare a standard T-diffuse uniform and extract color information using UV coordinates. But to preserve the effect chain, you want to work with the input color. That way you are building on top of the previous effects and not overwriting them. Once the shader is done, you create your custom effects and add it to the effect pass like any other. And there you have it. Hope you enjoyed this. Full code for this project will be on GitHub. My name is Francis. Happy coding, and I'll see you in the next one.